Today we are graphing and we are graphing a polynomial for the MAM1023S graphing video project. The question is to sketch the graph of the following function showing number 1 the domain, number 2 intercepts, 3 its symmetry, 4 critical points, and 5 inflection points. The function, as you can see, is 2x to the 4 minus x squared. So usually when I graph, I try to think of a few questions. Where is the function positive or negative? Where is the gradient negative or positive? And where is the concavity negative or positive, concave up or concave down? Where are the turning points and the points of intersection? Also, according to the question, we have to answer, is it an odd or even function? And the domain. We can clearly see from this, where the question is 2x to the 4 minus x squared, that it's a polynomial, and that means that the domain extends over all real numbers. So when we are solving for whether the function is positive or negative, we are looking for any solutions to the equation of 2x to the 4 minus x squared. And as we solve for this, we get that x equals 0 and x is equal to positive or negative 0.7. After this, we look at where the gradient, which is the first derivative of the function, so 8x cubed minus 2x is equal to 0. When we look at this, we get that x is equal to 0, and that another solution is that x is equal to positive or negative 0.5. It's very important for us to not forget the fact that it's a negative and positive because we solved for a square. The second derivative, which is 24x squared minus 2, has solutions of x to the positive or x is equal to the positive or negative square root of 1 over 12. And this is roughly or approximately 0.29. So before we start graphing, we have to have a type of representation with what our graph is going to look like. So all I've done here is put the critical points down for our graph and each of its derivatives. And from this, we can see whether the graph is positive or negative, what the gradient looks like, and what the concavity looks like. So all I'm going to do here is plug in values for each of these intervals that you see. And from this, we can establish what the graph looks like. So if you plug in a value less than negative 0.7, you will get a positive number. Between negative 0.7 and 0, a negative number. Between 0 and 0.7, another negative number, and then a positive number. If you plug in a value into the first derivative of the function, you will get a negative number if the value is less than negative half, a positive number between negative a half and 0, a negative number between 0 and a half, and a positive number where the function is more than 0.5. For the second derivative, where the function is less than negative 0.29, you'll get a positive number. And between 0.29 and negative 0.29, you'll get a negative number. And more than 0.29, a positive number. As you can see here, we've got changes in sign, because obviously we've got critical points here. But also, something that's very interesting from this is that you can see what the graph shape looks like. So because we know that the gradient is negative before negative 0.25 and then positive, we can say that the graph should have a shape like this, where the gradient is negative and then has a turning point at 0.5 and becomes positive. We can do something very similar here, except this turning point will now be a maximum because we're going from positive to negative. And we can do the same thing over here because we can see that it's negative to positive again, which means that it will have a shape like that. We can also say that because of our second derivative, we can look at concavity. And here the graph is going from concave up to concave down. And we know this type of shape involves something like this, because we've got an up and then a down. And similar here, except it's the opposite way around. We've got concave down going to concave up. And this goes with the idea that the graph is symmetrical about the y-axis. Because if you look at this, this is a mirror image of the other in terms of concavity. And now we can also look at symmetry. When you look at the symmetry of a graph, you are looking for whether it is an odd or an even function. So just as a reminder, to test if a function is even or odd, even would mean that if you put any negative value in for x, it won't change the function itself. If negative x is still the function of x, and this means if it's even, this means that it's even, and if it's even, it means that it's essentially a reflection across the y-axis. So if we can see here that if we substitute negative x in for where we would have x, we would end up with a function that is exactly the same as our original function. And this means that the function is even. So what we know about the graph is that it is essentially a reflection across the y-axis. So as you can see here, I've just put down where the intercept is on the one side, which is 0.7, as you can see here, where it changes from negative to positive. And I'm just going to do the same thing on the other side. On the negative side, we've got it's changing from positive to negative. So it's kind of because what happens at naught is where x is naught, but not crossing it. So it's most probably going to look something like this. Okay. At negative 0.5, the graph has a negative gradient and it's becoming a positive gradient. So we should have something that looks like this. We've got the same thing happening at 0.5, where the graph has a negative gradient and it's becoming positive. So it should also look something like this. And in terms of concavity, we've got at negative 0.29, we've got something that's going from concave up, which is this, to concave down, which is this. And the same thing is happening here, where we see it's going from concave down, which is negative, to concave up at the point of inflection, which is 0.29. As you can see, here's our graph. Note that I've labeled the intercepts with the axes and the x and y axes, also labeled the actual function, and just note the symmetry that you can see with an even function. And that's the graph. Thanks for watching.